All right, greetings everyone. The purpose of this video is to give you an additional example of finding a limit of a multivariable function. And this involves a technique that didn't necessarily show up on the other videos you may have watched. Okay, so here we're asked to find the limit as xy approaches the point 0, 0 of the function x squared times y cubed over 4x cubed plus y to the 9th. Now note, first of all, if I call this function f of x, or excuse me, f of xy here, that the point 0, 0 is not in the domain of this function, because if we plug it in, right, we're going to end up with 0 over 0, which is undefined. So we know the point, it does not lie in the domain of this function. So this is where we have to use some other techniques. One of those techniques, as you may have learned from the other videos, is to hold one of the variables constant in terms of the point we're approaching. So for example, I could hold y constant at 0, so say y equals 0. Plug that into the function. So everywhere I see a y here, I'm going to replace it with 0. So I'd have x squared times 0 cubed over 4x cubed plus 0 to the 9th. And then take the limit of that as the other variable approaches the number it's supposed to approach, which again, in this case is 0. You may notice if we take this limit here and simplify, first of all, the x squared times 0 cubed in the numerator is going to give us 0. The 4x cubed plus 0 to the 9th in the denominator is going to give us just 4x cubed. And so we're taking the limit as x approaches 0 of 0 over 4x cubed, but that 0 over 4x cubed will just simplify to 0, and taking the limit of that just equals 0. Okay, so it looks like if we hold y constant at 0, we get that the limit of this function as we approach 0, 0 is 0. Okay, well, let's look at doing the same thing with x now. So we're going to hold x constant at 0. So again, everywhere in the function where we see an x, we'll replace it with 0. So this will now become 0 squared times y cubed over 4 times 0 cubed plus y to the 9th. Take the limit now as y approaches 0 of this function, since we've already held x constant. If we do that, then this will become the limit as y goes to 0 of, notice that the 0 squared times y cubed just becomes 0 over the 4 times 0 cubed plus y to the 9th just becomes y to the 9th. And then notice that we again have 0 over something, so that'll just become 0. And taking the limit as y approaches 0 of that will again give us 0. So we're seeing evidence now the limit of this function approaching the point 0, 0 is 0. Okay, well, let's try another technique here. So another way to approach these is to set one of the variables as a function of the other. So I'm going to use the function y equals x, which we also have to make sure that the limit of this as x approaches 0 is also going to make y approach 0, so that it goes through that point 0, 0, which hopefully you would agree with me is true, right? If as x goes to 0 in this function y equals x, y will also go to 0. And then what we can do now is inside of our function f of x up here, or the given function, we can replace everywhere we see a y with an x. So this would now become x squared times, instead of y cubed, it'd be x cubed over 4x cubed plus, instead of y to the 9th, we would have x to the 9th. And again, since we've eliminated the variable y, we can now make this the limit as x approaches 0. Okay. And now we'll do some simplifying here. We take the limit as x goes to 0, the x squared times x cubed in the numerator would be x to the 5th over, and then we still have the 4x cubed plus x to the 9th in the denominator. And at this point, it might look like we're kind of stuck again, because if we were to plug in 0 here, we would actually end up with 0 in the denominator again, or we get 0 over 0, which is an indeterminate form, which we could then use L'Hopital to solve this problem. But that seems like that's going to be a little bit more complicated than probably what we want to do right here. So instead, what we might do is notice that in the denominator, we can factor something out. So that 4x cubed and the x to the 9th, so we'll factor out an x cubed there. So that'll give us, we'll have x to the 5th in the numerator over, factor out an x cubed in the denominator, so this will be 4 plus x to the 6th. If we do that now, we can cancel out some of the x's down here, or all the x cubes down here with some of the x's in the numerator, give us an x squared in the numerator. So we're now taking the limit as x goes to 0. We'll have x squared over 4 plus x to the 6th. At this point, notice now we can plug in 0 into this function. And if we do that, we're going to end up with 0 in the numerator. So giving us a final answer just of 0. Okay. So now we've done this limit 3 different ways, and each time we've gotten 0. So we might be thinking, all right, the limit here is probably 0. However, if you take that and plug it in to WAMAP, if this were a WAMAP question, unfortunately, WAMAP would not give you that nice green check. It'd give you that ugly red X. So we need another approach here. And what I'm going to do is I'm again going to, or to see why that is, I should say, I'm again going to write y as a function of x. But this time I'm going to choose a little different function. So here I'm going to use the function y equals the cubed root of x. Okay. And hopefully it'll be clear as we go through this why I chose that. You can always ask me later about that. And let's first of all think of, as x goes to 0 in this function, will that make y go to 0? And the answer is yes, right? As x gets closer and closer to 0, the cubed root of x gets closer and closer to 0. So we'd be getting 0 as our value of y. So this function does still allow us to approach the point 0, 0. And now in our limit, everywhere we see y, this time we're going to replace it with cubed root of x. So what we would end up with here is x squared times the cubed root of x cubed over, we'll have 4x cubed plus, and then instead of y, we'll have the cubed root of x to the 9th. And then we're taking the limit of that now as x goes to 0, since we've eliminated the variable y. Okay. Let's look at simplifying this. So we have in the numerator, or sorry, we're still going to be taking the limit here as x goes to 0. In the numerator there, we're going to have x squared times, if you recall, taking or cubing the cubed root of something will just give us the something under the cubed root. So this will just become x over, we still have 4x cubed here plus cubed root of x to the 9th. One way we can simplify this is we can rewrite cube root of x, as x to the 1/3, and having that all raised to the 9th power. If we think now about our powers of exponents, we have an exponent to an exponent. We multiply them. So 1/3 times 9 gives us x to the 3rd. Okay, so the cube root of x to the 9th equals x to the 3rd. This will be x to the 3rd here, which notice looks like it might work out kind of nicely because we have an x cubed there. So let's rewrite the limit one more time. So the limit as x goes to 0 of, simplify some more, we'll have x squared times x in the numerator becomes x cubed. 4x cubed plus x cubed in the denominator becomes 5x cubed. And now we've got something we can simplify some, because we have the x cubed in the numerator, x cubed in the denominator. We can cancel those out. And so then this will become the limit as x goes to 0. And our function now will just be 1/5. So we're taking the limit of a constant. And in that case, we get 1/5. All right. So notice in this case, by letting y equal cube root of x and approaching the point 0, 0 along that path, we got something other than 0, right? We got 1/5, which tells us that the limit from this direction is not the same as the limit from other directions, which tells us that this final limit here does not exist. Because remember, in order for it to exist, the limit needs to be the same coming from every direction. All right, that's it for now. Thank you for watching.